I don't want to, like, if we continue this conversation much longer, we're going to have to put it on TikTok because this is apparently where people discuss the philosophy of what is math. But it's like...
You're listening to Marianne Writes a Programming Language. And I'm Marianne. The first thing every guest has asked at the beginning of every interview is, what exactly are you trying to do? So I figured before we get into the details of how to do it, I should spend some time answering that question in detail. Talking with me today is Hillel Wayne. I met Hillel a few years ago at one of my all-time favorite tech conferences, Strangeloop. Hillel is, well, I'll let him introduce himself.
My name is Hillel Wayne, but I go by Hillel Wayne almost exclusively. I am an ex-physics major, ex-web dev. Now I teach formal methods, the science of writing software blueprints in a way that can be verified directly as opposed to after you build the system full-time. I also do a lot of writing on tech culture, tech history, and sort of the journalism and sort of culture of tech. So I sort of end up at this point, my job is mostly a mix of teacher, historian, journalist, and writer.
The science of writing blueprints. I like the way he puts that. But there's been something that's been bugging me about formal specification for a while now that fuels this project. How to keep people from misusing them. People gravitate towards models, much like statistics, because they feel like it reflects objective truth. If you're looking to build models because you want to help reason about the world, your system, and decisions we face with both, then just any modeling language will do. Hell, Python will do. But that's not what a lot of people look for when they model things. They don't want an abstraction. They want a guarantee. For that reason, formal specification stays on the fringes of software engineering. Unit tests feel like they offer a guarantee. Models of software systems, on the other hand, can run correctly as specs and then be subsequently built very differently from their model. Or the spec itself can miss some critical factors and proving it just wastes a whole bunch of time. My interest isn't in offering that guarantee, but in creating a value add that diminishes the desire for a guarantee in the first place. I want to have a modeling language where the whole purpose of writing a spec is to generate a failure. Or this is the way I explained it to Hillel.
What I'm really interested in is system resilience. Mm-hmm. And this idea that systems have a certain amount of complexity and they have a certain amount of coupling. And then it's not about optimizing for minimum complexity and minimum coupling. It's about having the right amount in the right places for the system. And so being able to sort of like spec out a system so that you could see where it's complex and where it is coupled, and then look at how much leeway you are giving yourself on your inputs before the system produces an output that is not what you want, right? Mm-hmm. So I sort of like, this was sort of the reason why I gravitated towards formal specification, because it seemed to have those dynamics. And then it took me a long time to figure out, oh no, the reason why it's frustrating is because this language is built on the idea of mathematical correctness, on this state never being true. And I actually don't care if it's ever true. I just want to know, like, what are the parameters? Like, when will it get to that state? And like, how brittle is it? And if we change it in this way, does it become more brittle or less brittle, right? Mm-hmm. So that's sort of, there are languages that do this, but they're by and large proprietary, or they're based entirely on being able to visualize systems.
Wait. We're throwing around a couple of different terms that may be very foreign to you. Hold on a second.
So now, like, the first thing that I have always wanted to know is formal specification, formal methods, formal verification. Are all these terms synonyms, or is there like an umbrella hierarchy between them, or how would you describe it?
And this is where it would have been really nice if I'd managed to, I just recently moved to a new place, get my whiteboard up and running, so I could draw the little charts for you. But so
this is a podcast, so the little charts wouldn't help anybody.
Well, it would help you understand.
Okay.
So one thing to keep in mind is that, like, sort of anything involved in tech, there's a lot of different communities doing a lot of different things in the space at different times. So you often see terms that sort of bubble up that certain groups use. that other groups use a different term, and then sort of they get smushed together in weird ways.
Mm-hmm.
This is a highly broad overview, incredibly inaccurate, but it's a good enough lie to go on for now. Formal methods is just the broad field of anything involved that is called formal methods. Formal specification is the art of writing rigorous descriptions of what something should do, either what a design should do or what specific code should do. So you write a formal specification of a design using, say, a TLA plus, or you write a formal specification of code using, I don't know, Spark or like Idris. Then formal verification is the art of taking the thing and taking the specification and showing they're connected.
When he says showing they're connected, the typical way to do that is to write a spec that is parsable and can be compiled into an executable model using first-order logic. I've written about first-order logic before. See my blog post, The Subtle Power of Booleans, to get up to speed. But basically, you can think of first-order logic as a puzzle using true-false statements. If A is true and B is true, then C must be false. That sort of thing. The way this works in formal specification is that the spec defines what the system is doing and a set of assertions about what states should be impossible. So, for example, here's how my system validates and approves transfers of money between accounts. Check that there is no order of events that result in a negative account balance. If this sounds super impressive, I should point out that I'm actually really bad at it. No, really. Part of the reason Hillel and I became friends is because he spent so much time helping me fix silly problems with my specs when I started.
I have a really hard time thinking of logic as being math. Every time I'm always exposed to it as like a math concept. And then when I dig into it, I think to myself, this is kind of more like, I don't, it's not fair to call it philosophy, but like, it doesn't feel like math to me. And I'm wondering if I'm missing something there. If it's like,
can you explain why it doesn't feel like math to you?
I think because I tend to see it as being about relationships, not about numbers, right?
Mm-hmm.
You know, like you have a set of certain things. Do they all have the same properties, right? Or
are you familiar with Seven Bridges of Königsberg?
I am familiar with Seven Bridges of Königsberg.
Is that math?
No.
Okay. It's category theory math.
Yeah.
What
is category theory?
Okay, cool. We can skip that. So this is something that I actually am very adamant about, because I think that there's this really weird divide in like programming, where you have basically two camps, essentially. You have the people who are like, we don't need math. Math is like pointless unless you're working in specialist domains. You have the people who are like, math is beautiful and shows you the underlying like abstractions of programming and how everything is secretly a type. And then how there's like blah, 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 blah. And I think that there's the third camp, which is the camp that I belong to, which is that math is directly useful to programmers in day-to-day life. But the problem is that the math that is sort of presented as math by both camps is a very small slice of what math is, because math is fundamentally a language we've developed to explain things.
Mm-hmm.
And almost everything in math comes from one of two places, either trying to build tools to model reality better, or to build tools to model the tools that we just built better.
Yeah. So I think it's less, do we need math, or how much math do you need to be a programmer? And more, there is this cultural and psychological and emotional context around math as a subject, right? So what you're saying before about how some people find the specifying of designs unsatisfying because it doesn't connect to the code, right? It's the design process. I think that's because people take a false sense of security in math, right? They think like, well, it's math, ergo it's the truth. There are no opinions. There is no subjectivity at all. Like, it's math, ergo I don't have to defend myself.
I think it's more just that because you can't automatically translate it into code. You have to do that manually, and then you can make mistakes.
True, but like that goes back to it. Like, well, you could have made mistakes when you wrote the design in the first place. You probably did make mistakes when you wrote the design in the first place. But there's that feeling of like, I ran it, and the math proved to me that it's correct.
Right.
And I think there's the other side of it, that people are also super intimidated by the math, and so to take something like first order logic that is a very different fish from, let's say, algebra, and putting it under the heading of math, I think
we're talking about
people,
algebra over, for the record, just because I am a math head. We're talking about algebra as in like high school algebra, right?
Yeah.
Not like algebra as in college algebra. Okay.
Yeah, as in high school algebra.
Polynomial rings. Algebra over polynomial rings. Finite polynomial rings.
All right, you give up. You win. I think
just be precise here.
Creates people self-select, right?
Right.
People for whom first order logic and similar concepts would be extremely valuable in the practice of their discipline. Avoid it because they're told that it's math, and they assume that all math is like what they learned in high school that they found difficult or confusing or unpleasant, right? And it's like, sometimes I don't want to, like, if we continue this conversation much longer, we're going to have to put it on TikTok, because this is apparently where people discuss the philosophy of what is math. But it's like, I do feel very strongly, like, why are these concepts considered math versus philosophy, for example?
Well, for a long time, science was considered philosophy.
Really? When did it make the switch from being something other?
I think it might have been the 1800s when it stopped being natural philosophy and became science.
Yeah.
I forget the exact details, and for a long time, math was philosophy too. And a lot of linguistics used to be philosophy of language. Like, philosophy essentially is just this big, like, miscellaneous bin where we shove everything that we don't know how to classify into other disciplines. And that's
doctor of philosophy, right?
Not nice to philosophy and like rude to philosophy, but like, there is not as much difference between philosophy and the disciplines that spawn from philosophy as we tend to think.
My mind's been lingering on the edge of this problem. A few weeks ago, I discovered some literature I had collected on the Cybernetics movement of the 40s and 50s. Cyberneticians were very into modeling systems. They believed everything could be modeled as systems of feedback loops and potentially quantified. From a modern perspective, when we think of math and science as truth and human behavior as faulty, variable, inherently illogical, emotional, and biased, cybernetics seems like a pseudoscience. But this assumes that math is objective and that its precision comes from natural laws that themselves are mathematical. In other words, did humans invent math, or did humans discover math? But what if math isn't infallible? For example, we can't really accurately represent pi, but for most cases 10 digits is precise enough. So all calculations done with pi have some sort of rounding error built into them, but that never seems to matter. In 2010 at the World Science Festival, astrophysicist Marianne gave a full set of other examples.
There was this astronomer Johannes Kepler, and he made observations 400 years ago, and they were not very accurate. They were accurate for his time, but not very accurate. They were accurate to within about 4%. Yet from those relatively scanty observations, Sir Isaac Newton managed to write a mathematical law of gravity that already by the 1950s was shown to be accurate to better than 1 part in a million. In fact, in an experiment done in 2008, they showed that the inverse square law of Newton holds down to a distance of 56 microns. 1 micron is 1 millionth of a meter. These are distances that Newton could have had no idea his mathematical law should hold true. What is it that gives mathematics such powers? We have a theory of everything that's electric and magnetic. It's called quantum electrodynamics. In this theory, it's a very highly mathematical theory. Electrons that move in atoms, they are like little magnets. You can use this theory to calculate the strength of this magnet. We can calculate the strength to parts per trillion. You calculate this magnet to parts per trillion. In 2006, this magnetic strength of the electron was measured to parts per trillion. And the two results agree to within 8 parts per trillion.
What I really love about that clip is that Dr. Levia talks about those things to convey the awesome, impressive accuracy of math. But people like me hear it and think, wait a minute. So if you go smaller than that, does math just stop working? What we like to think of as mathematical laws that govern the function of the universe are abstractions that eventually break down at some point. But the point in which that breakdown occurs is at a scale so tiny that for most practical applications of math, the probability of it mattering is insignificant. If you throw a dart At a dartboard, it doesn't matter where you hit the bullseye, just as long as you're within the boundaries of the bullseye. Mathematical precision is a natural process of science's maturing. As we continue to study, we make more observations and group them in patterns. Eventually, we begin expressing those patterns in math. We continue to document more observations, refining the math until it reaches a level of accuracy in which the gap between the abstraction we've created and the quote-unquote reality is irrelevant. What gives math its magical quality is that occasionally the mathematicians develop the model before the reality they are modeling has been observed. In my opinion, building models looking for correctness, proofs, and guarantees is the wrong way to model. Models should be thought experiments, letting us test the relationships between various abstractions so that we know where to look for real-world observations for further study. But I also believe that technology suggests to its users how it should be used. So if users are using modeling languages as proofs, it might be because the languages themselves encourage that behavior.
The biggest barrier by far to formal methods adoption, at least on the design level, is UX.
Yeah.
If we could improve the UX,
what I find really interesting, I'm going to interrupt you for a second, sorry. What I find really interesting about UX is that it is inherently subjective, right? Like I found TLA Plus's syntax to be really, really confusing and hard to like grasp what it was trying to get me to do. And then hard to remember. It was like, it had to be like just straightforward memorization on some of the stuff. And then I started like in a different train of thought for a different purpose. I started learning first order logic. And as soon as I started learning first order logic, I kind of went, I understand. I understand why the syntax is the way it is. It's like you have basically taken a user experience of first order logic and put it into a programming language. And that is why you want me to write these things the way and now I understand all of the errors that sort of came before. So I feel like if you were coming from the perspective of having a good foundation in first order logic and maybe some other aspects of formal computer science or math, that you would look at TLA Plus and go, oh, I'm very comfortable in this medium. Whereas you're coming from, I just graduated from a boot camp, or I'm a self-taught software engineer, and like the stuff that I'm familiar with are Python and Ruby, you would look at TLA Plus and go, what the hell is this? And why doesn't it work the way I think it should?
So your basically argument is that like TLA Plus syntax might not be an issue. It's more of just the background you have.
I think I'm arguing that there is no such thing as like good UX. It's very conditional based
Here's
on
my counter
like
proposal.
what you're exposed. Yes.
Running TLA Plus from the command line and having the output error output as a JSON you can pipe into some other tool.
And what would that other tool be?
Well, people could build other tools. It could be something that made it easier to sort of explore. You could have it be a visualizer. You could have it be like, pump it back into like a language server provider, so that way you can have the errors appear in your, in your editor, having the ability to just like step through it step by step, or like drop it into a table. Like that's the UX I'm talking about. Command line tooling, like better error messages. When you get a syntax error in like pretty much any formal method that I've used, the errors are always very, very like obtuse.
Yeah.
That could be improved dramatically.
Right.
When I say UX, I don't mean like using mathematical symbols, which I personally strongly prefer, to using programmatic symbols, which a lot of programmers find easier. I'm talking about things like not having to use the IDE, being able to script out running multiple models, bash script, things like that.
Okay, cool. Yeah, no, that's fair.
You've been listening to Marianne Writes a Programming Language. Just a quick reminder that patrons get access to all my extras. My conversation today, for example, covered so much more ground than what's in this episode.
Lesson learned. Just learn linear algebra and apply it to literally everything.
Yes.
You'll be good. You'll be good.
Matrices solve everything.
Okay.
More matrices.